Hey everyone, in this video we're going to be doing another equations of motion problem. The problem that we want to look at, the mechanism, is a block inside of a groove. Through the center of that block is a pin joint, and connected to that block is a pendulum. So what do we want? We want the equations of motion. What are we going to do to get these equations of motion? We know that we have to take Newton's second law and Eulers' second law, sum of moments, there we go, ddt of h, and I'm going to do a plus dot 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 on this because depending on where you take the moments about, you could have some additional terms. All right, we know that we need to construct these, and in order to construct these, what does it take? It takes kinematics and momentum. So kinematics and momentum. That's going to help us define the right-hand side of this. Next, we need to do free body diagrams. From the free body diagrams, we have to construct the sum of forces and the sum of moments equations. At that point, we have both sides of these, which means we can put them together. We can make the Newton-Euler equations. And then the final step in this process, there's going to be some unknown reaction forces in these equations initially. We need to eliminate any unknowns. So this is the process. Anytime that you want to find the equations of motion, this is going to be your process. Now, what do we know about this problem ahead of time? Well, just looking at it from observation, what can we say? We can see that there are two rigid bodies. There's going to be two generalized coordinates. And those generalized coordinates are, there's a translation variable, q, and then there's a rotation of the pendulum, theta. Now, that q and theta are independent of each other. You could lock the pin joint, and you could make the block move. We could hold the block in place, and we could freely spin the pendulum, which means there are 2 degrees of freedom. These two motion variables are independent of each other. We're going to look at this as a planar problem. We're not going to worry about translation in and out of the board. We're not going to worry about moments in and out of the board. So as a planar problem, if we construct these sum of forces and sum of moments, we're going to get 6 scalar sum of forces, sum of moments equations. If there are 6 equations and there are 2 unknowns, in this case, unknowns that you can solve for, 2 generalized accelerations, that means there are 4 other, you could think of them as constraints. They're not going to be constraint equations like we've been doing vector loops and things like that, but these constraints are the reaction forces. And reaction forces are what, reaction forces, there we go. If you think about constraints as not just vector loops and rolling constraints, but just the joints themselves take away degrees of freedom from the problem. So this block is not in free fall because it's inside of the groove. And the groove prevents the block from translating in the vertical direction. It also prevents the block from rotating. So this groove, this joint between the block and the ground, it has taken away 2 degrees of freedom from the block itself. And it does that through reaction forces. Similarly for the pendulum is able to rotate, but it cannot arbitrarily move left and right or up and down. So there are 2 more reaction forces. So it's going to be a total of 4. All right, we can basically see where the problem is going. Just by observation, we can have all of these expectations laid out ahead of time. So let's clean this up and let's get started with the kinematics. Let's start with the diagram. We know we need points N. Let's call the center of the block point A and center of mass of the pendulum point B. Of course, frames. The A frame doesn't rotate, so it's going to be aligned with the end frame. Here's the end frame. And the B frame. So XB is along the length of the rod. Kinematics. Let's do the rotations first. So the A frame does not rotate. So I'm going to say omega in A dot equals omega in A equals 0. Next, the B frame. Well, omega into B is theta dot ZB, and omega into B dot is theta double dot. And I'm not going to go through the formal definition of the rotation, but the rotation from N to B is a simple rotation about a shared z-axis, motion variable theta. We know how to define this thing. Next, the linear acceleration of A is going to be q double dot x hat n. Again, I'm skipping some steps here. At this point, I expect that you can do these kinematics quickly. And the linear acceleration of B is going to be q double dot xn. Let's call this length L1. So plus L1 theta double dot YB minus L1 theta dot squared XB. There we are. And again, if you are struggling with this, go back and look at your kinematics again. All right. So this is good. Moving on. Next, let's talk about the momentum terms and how we want to construct our equations. For body A, of course, the mass of A is known. We're going to assume symmetric geometries, so the inertia terms are going to be known. And also on both of these, it's going to be diagonal only. If we assume that the bodies are axisymmetric, then, for example, IBB is going to have an XX term, a YY term, and a ZZ term, and the rest of these are going to be zeros. So sum of forces on each of those, easy. Sum of moments, for body A, let's take them about the center of mass, point A. And for body B, let's take them about the pin joint at A. So that means we're going to need IAA, and we're going to need IBA. Now IAA is known, and I just had IBB up there. So IAA is going to be the same thing, diagonal only. Numerical values will be different. Now IBB, IBA is equal to IBB plus MB, and the displacement dyadic from A to B, which is itself a function of the position vector from A to B. Sorry, reverse this, B to A, B to A, yeah. All right. So what is this at the end of the day? Once you've done all of these modifications, I'm going to skip right to the answer. Again, this is not a video on parallel axis theorem. At this point, you should know how to do it. MBL1 squared. There we go. So here's the modified inertia matrix. I took the original IBB and I modified it with parallel axis theorem. So this is what we get at the end. And of course, this IXX, IYY, these are different than the IXX, IYYs for body A. So later, I'm going to put some additional lettering on these to show that this came explicitly from the BB matrix. Okay, so we got momentum taken care of. Next, let's do free body diagrams. We have two bodies, A and B. Free body diagram for A and free body diagram for What's the easy stuff? We know that there's gravity acting on these. So minus MAG and minus MBG. Next, let's say that there are some external forces in this problem as well. Let's say that there's an electric motor that has been mounted onto block A that is threaded onto pendulum B and generates some kind of external torque. So let's apply a positive torque to body B, and because of Newton's third law, action-reaction, if it's generating a positive torque on B, there is a reaction torque on A, and that one is negative. Let's say that, what else? Let's say that there's friction acting on body A. Okay, so after this now, it looks like there's just reaction forces are left. So let's do reaction forces at the pin joint. So this is R1X, R1Y. There's also a reaction force between the block and the groove. So let's do that one as up. Let's call this R2. And then there's also the reaction moment preventing the block from rotating. And I'm going to do this one as a positive moment, R3. So that takes care of the block. As far as the pendulum goes, there's just the reaction forces at that pin joint. And if we did them positive on the block, then we need to do them negative on the pendulum. So this is R1X and R1Y. Okay. Let's, I'm just going to give myself a little bit of room to write the equation. So I'm going to shorten this diagram just a little. MBG. Okay. So underneath these diagrams, let's start writing the equations. Let's start with body A. We need the sum of forces on body A. What we're going to find, just cutting to it, what we're going to find is that not all of these equations, not all the scalar versions, are actually going to be necessary. Consider that in order to finish, perhaps we don't need to know or need to have expressions for every single one of these unknown reactions. Let's just see how it all comes out. But we're going to approach this by doing all of the sum of forces and moments. So sum of forces on A. Let's do stuff in the X direction. We've got R1X and FC. That's in the X hat N. And then we've got R1Y plus R2 minus MAG. And that's in the Y hat N direction. Okay, yeah, that looks good. Tick, 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 tick. Gotcha. Next, let's do sum of moments on A. And we're going to take these about point A, so the center. By taking them about the center, consider how many of these have no moment arms. The reaction forces R1 and R1X, R1Y, these act at the center, so no moment. We're going to say that R2 is acting through the center, even though I drew it a little bit off center. So no moment there. Gravity, of course, is acting through the middle, no moment. So what does that leave? That leaves this external torque, that leaves the reaction moment, and it also leaves the friction term. So we're doing positive torque on the pendulum. That means it's negative torque on the block, so negative tau. Let's do Z hat A. Next, let's just add in this reaction moment, R3. And then we need the moment created by the friction force. So let's do the position vector from A. We need the point that's in contact. So we can put a point down here on bottom. We can call that point C. So the position vector from A to C cross, and the force is acting in the positive direction, so FCXN. Now, what is this position vector? this position vector is, we're going down. It's a fixed distance. We did L1 for that. Let's do negative L2, y hat n, cross FCXN. So this cross product, when we evaluate it, y cross x is negative z. There's a negative in front, which makes it positive. So plus L2FC in the z. Now we could write it as Zn. Consider that Za is Zn, so Zn, Za, it's the same thing. Za. All right, let's take a look at this, and let's just make sure that it makes sense. We have assumed a negative torque. There's a negative torque. We've assumed a positive reaction. There it is. And with the direction of the Coulomb, the sliding friction that we've assumed being positive, and it acting on the bottom of the block, that creates a positive moment about the center. So this is currently positive. Now, if the block changes directions and the direction of the Coulomb friction changes, okay, then this takes on a negative value and the direction of the moment reverses as well. So that takes care of it. Good. So we got forces and moments for A done. Let's do forces and moments for B. Sum of forces on body B. Now this one's pretty simple. We've got a set of reaction forces and we've got gravity, that's it. And since they're positive on the block, they are negative on the pendulum. So negative R1x, x hat n. And then let's group these together. So minus R1y minus mbg, y hat n. Now, one comment before we move on. I, of course, did the reaction forces in the N frame. You don't have to. You could have done reaction forces in B frame if you wanted to. I have an idea. I know where this problem's going, so that's why I did it in N frame. But if you're consistent and careful, you can put these in B frame just as well. All right. Let's do moments. We said that we're going to do the moments on the pendulum about the pin joint. Because we're doing it about the pin joint, these reaction forces create no moments. Makes it easy. But the gravity does create a moment. And of course, we still have this external torque. So the moment on B about point A, it's equal to, I'm going to bring the torque down. It's positive on the pendulum, so it's just tau ZB plus. We need the position vector. Now we're taking the moments about A. So we need the position vector from A to point B, B being the center of mass, cross minus mbg in the y hat n direction. So what is that position vector? Well, this position vector is L1 x hat B. Well, if we do L1 x hat B cross minus mbg y hat n, that's a B frame cross an N frame. So we actually need to take this, we need to put it in the N frame. So instead of doing L1xb, let's rewrite it as L1 times cosine theta xn plus sine theta yn. That, of course, comes from our definition of the rotations. So it's this position vector cross minus mbg yn. So let's resolve that cross product. Y component cross y component is going to be 0. We're going to have x cross y. X cross y is positive z. There is a negative in front of this, which is going to make this term negative. So negative L1 cosine theta mbg. And let's group these terms. This is all now about the ZB axis. ZB, of course, is equal to ZA. equal to Zn. Does this make sense? Well, looking at the diagram, of course, we just assumed that that was positive, so it's positive. Look at how the gravity is creating a moment. That's what this term is saying. It's saying that the gravity creates a moment specifically about the pin joint. Now, in the current orientation, we can see that this gravity is creating a negative moment. It's making this thing want to turn. But consider that this term is actually a function of cosine theta, which means depending on the orientation of the pendulum itself, this could create a positive or negative moment. We know that this is just a scalar. We know that g is a scalar. We know that L1 is a scalar distance. So the MBG L1 is always positive, but the cosine theta will change. So currently we've drawn it in quadrant 4. We could draw it in quadrant 1. We could draw it in quadrant number 2. In quadrant 1 and quadrant 4, the cosine is the same, and the gravity is going to create negative moments in quadrant 1 and quadrant 4. But in quadrant 2, this is going to create a positive moment. It's going to want to pull it this way. Well, also in quadrant 2, cosine is negative. So once theta moves into quadrant 2, cosine goes negative, and that negative comes out front, creates a positive, and this creates a positive moment. So this equation is good. All right, where do we need to go from here? We've got sum of forces, we've got sum of moments on both of these things. Now we need to start putting these together and forming our Newton-Euler equations. So here's what I'm going to do. I'm going to clean this up and erase, and we're actually going to start with the pendulum. So let's take this sum of moments equation that's in front of us right now, and let's turn this into Eulers' second law for the pendulum about the pin joint. The sum of moments on B about A, this will be equal to negative MB, the position vector from B to A, cross VA dot, plus IBA omega into B dot, plus omega into B cross IBA omega into B. Where does all this come from? This is Eulers' second law for a body about an arbitrary point. So you can see there's components arising from the angular momentum about that arbitrary point, and then there's this additional term. If you don't know where this came from, then you need to go watch the video that's Eulers' second law part 3, where I talk about this. So this equation is equal to this expression that we've written down on the bottom. The expression on bottom, notice that this expression is actually finished. There's nothing else we need to do with this. Torque is specified, and then all of these are either known quantities or they're functions of a coordinate. So there's no reaction forces or unknowns in this expression. So we're actually done with this part, so we can just hold on to this. Let's talk about what's going to happen with these bits on top. Even though this inertia has been modified, we know what it looks like. We've already written it down. We know it's diagonal only, and we know that we are performing a simple rotation about a single axis. Because of that, you can go through and you can do the expansions on this, and you will find that that term is equal to 0. We've also, since we've already defined IBA, you can take IBA and you can do the dot product against omega into B dot, and that's a fairly simple multiplication. So really all that's left is we just have to sort out this term on top, this cross product. So let's do that. I'm going to bring this up. So tau minus L1 cosine theta MB G, this quantity in the ZB, equal to. This one's 0. We know what's going to happen with this term. I'm going to go ahead and write it down. We're going to get the IZZ BB term plus MB L1 squared times theta double dot, and that is also in the ZB. So here's the sum of moments. Here is inertia times change in angular velocity, and we still have this one to contend with. So minus mb, the position vector from B to A is negative, right? Because we're going against the xb, so it's negative L1 xb, and then we need to cross it with VA dot. In a lot of these problems, when we take a parallel axis theorem, we're doing it about a non-moving point. So if you're thinking about a non-moving point, that makes this pretty easy. VA dot would be 0 in that case. In this case, the acceleration of A is q double dot x hat n. So we need to resolve this now. What are we going to do? Well, this is in the B frame and this is in the N frame. So we need to put this into the N frame, or alternatively put this into the B frame. What is that in the B frame? Well, one thing I'm going to do is I'm going to cancel these negatives. So underneath I'm going to write it as plus MB. This is L1 cosine theta xn plus sine theta yn cross q double dot x. So let's take care of this cross product now. We took care of the plus, no, we took care of the negative, so now it's plus. This is in the x direction, so the x component cross x is going to be 0. We're going to have a y component cross an x, and that's going to end up being negative z. So this is back to being negative, and it's minus mb L1 sine theta times q double dot. And this is now in the zb direction. Let's take a look at this equation. There's some interesting things going on. I'm actually going to rewrite this just underneath. And what I'm going to do is I'm going to put these inertial terms on the left-hand side, and I'm going to put that one on the right-hand side, and I'm going to organize it in a particular way. Let's think of if we wanted to list the generalized coordinates, we listed them earlier as q comma theta. So if we were to put these in a vector, we would put them in as q theta. We could reverse the order. It's however you want to present these things. So there's the generalized coordinates. If I wanted to present the generalized accelerations, well, that's just q double dot and theta double dot. So we're going to get to how that affects this in a few minutes once we finish. But for now, let's organize the equation according to q first and then theta. So we're looking at minus mb L1 sine theta q double dot. And I'm actually I'm gonna pull the q double dot out, and let's put these in parentheses. So q double dot, there we go. And then it's plus izz from bb plus mb L1 squared, and that's times theta double dot. And then we're equal to tau minus L1 cos theta mbg. And I have dropped the z's. So do a dot product with the z, and you get the scalar version of this. Okay, let's look at this equation. Are we done with this equation? Well, as we go through it, realize that everything inside of these terms is now known. All of these terms are known. The only thing that is unknown in this equation is the q double dot and the theta double dot. These are actually the things we want to solve for. These are the generalized accelerations. The point in building the Newton-Euler equations, most of the time, is to find the accelerations. Now, there's a problem. There's two of them. It's a q double dot and a theta double dot inside of one scalar equation. And we don't have a constraint in this problem. We've seen other problems with constraints where we could maybe solve for q double dot in terms of theta double dot, something like that. If we had a kinematic constraint, we could eliminate one of these using that constraint equation. But in this case, we don't. Because remember, this problem actually has 2 degrees of freedom. These two things are independent. Because there are two unknowns, the unknowns being these generalized accelerations, because there's two of them, we actually need a second equation. We can't solve for both of them using just this equation. What you will find is if you have 2 degrees of freedom, you need 2 equations. If you have 3 degrees of freedom, you will have 3 equations at the end of the whole process. So we are halfway done at this point. We've only gotten 1 equation. And one thing to note is that really this is the equation associated with the rotation of the pendulum. It does have the translation of the block involved, because really this translation of the block is the movement of this pin joint. And if you can imagine this thing accelerating, that would affect how this pendulum would move. It's akin to if you wanted to balance something in your hand. And let's say that this thing starts to tip, and I can attempt to correct the balance by moving my hand underneath it. And you could do it with a pen, you could do it with a ruler or a broomstick or something. So that's called an inverted pendulum problem. And you can balance this pendulum by moving the base underneath it. And you can do that with actually without a torque. So consider if there were no external torque in this case, and we actually wanted to hold this pendulum upright, we could actually move the block back and forth. We could put a motor on the block, just translating it, and we can control it. And those are fun experiments. You could Google these or go find somebody on campus who has one built, and you can actually build those systems, the inverted pendulum balance systems. So this equation is really associated with the theta double dot, and I pointed out because notice there's no mass or inertial properties in this equation for the block A. All of these properties that we're looking at, the mass of B, the inertia of B, gravity from B, right? So what we need is we need to go back and look at the equations for body A and see how can we bring in the inertial properties of A. Well, that means we're going to be building an equation for theta double dot, and theta double dot's the translation. So let's clean this up a bit, and let's go back and let's look at those equations. I've rewritten the sum of forces on body A, and I've written Newton's second law for body A. We know what the right-hand side of this is, ddt of Ka, well that's MAVA dot, and for this problem that's going to be MA Q double dot X hat N. We could take these two equations and we could set them equal to each other, the right-hand side with the sum of forces, the left-hand side with MA Q double dot X hat N. If we want to isolate this, we want to make it a scalar equation, we need to do a dot product with the X hat N direction. So that yields MA Q double dot equals R1X plus FC. Well, here's Newton's second law for that block in the X hat N direction. It has the Q double dot in it. Friction term, that's fine. We can always write an expression for the friction term. But this one has R1X in it. It has a reaction force. And we know that we need to eliminate this reaction force before we're finished. At this point, we're not done. So how can we get an expression for R1X? Well, we actually have to go back to the pendulum and we have to look at sum of forces on the pendulum. So let's do that. Let me copy these down. Here's sum of forces on B. We know that it's the reaction forces at the pin joint and gravity. We know that the sum of forces on B is equal to ddt of KB. Now, ddt of KB is a little more complicated. It's B multiplied by Q double dot XN plus L1 theta double dot YB minus L1 theta dot squared XB. What we are trying to do is we're trying to get an expression for R1X that we can substitute into the equation above. If we take the sum of forces and we dot it in the X hat N direction, that's going to give me just the R1X on one side of the equation because these are both going to be gone. So let's do that. Let's say R1X equals. We've taken these equations and we are dotting it in the X hat N direction. What does that yield on the right-hand side? Well, we've got mb multiplied by q double dot plus. Now, we still have something of these, right? Because this is B frame, and then we have to rotate the B frame into the N frame, and then we're going to keep the X hat N component. So when you do that, here's what you're going to get. You're going to get minus L1 theta double dot sine theta, and minus L1 theta dot squared cosine theta. Yeah, okay. And this is actually negative R1x. There we go. Don't forget about that. Okay, so what are we going to do now? We take this and we put it into this equation. And we can address this negative. I can just make this positive. I can put a negative here, positive, positive. So let's take that now and let's put it into the previous equation. And here's what we're going to get. MA Q double dot equals, I'm going to bring this directly up. Let's bring over the FC first, and then plus MB multiplied by L1 theta double dot sine theta plus L1 theta dot squared cosine theta minus Q double dot. Let's take a look at this equation. What kind of shape is this equation in? Are there any unknowns? Again, there's the Coulomb friction. We could always write an expression for that. In fact, we can just do that now. Your Coulomb friction is going to be equal to minus mu times the absolute value of the normal force, which was R2, and then the motion of the block is positive in that direction, and that's Q. So Q dot divided by the absolute value of Q dot. There you go. There's your FC. So what I recommend is don't take this and put this in here right now because it's just too much. I tend to just take these terms and set them off to the side. And then when the rest of the heavy lifting is done, I go back and I take these and I put them back in. Now, as for everything else, mass is known. Coulomb is defined, mass is known. Length, sine, length, cosine, and everything else, the theta dot, that would be known. The only unknowns are these accelerations. And the reason I say the theta dot and the thetas are knowns, if you have an equation where you can solve for accelerations, consider that you can integrate that and get the velocities. If you have an equation for the velocities, you integrate that, you get an equation for the positions. It does require that you have initial values for the theta dot and the thetas. You integrate the Q double dot to get Q, integrate that to get Q dot, integrate that to get Q. You have to have initial values for this speed and position as well, but that's just the nature of solving differential equations. You have to have the initial conditions. So there are no unknowns here other than the Q double dot and the theta double dot, which is the same situation we were in moments ago with the previous expression. So let's take this and let's clean it up a little bit and let's put it in a similar form to what we had for the other equation. So we're gonna bring all the unknowns to the left-hand side, and then we're gonna group them, and we're gonna group them starting with the Q. So we have MA plus MB, Q double dot. The theta double dot term is gonna be negative. So this is now minus MB L1 sine theta, and here's how I'm actually going to write it. I'm going to do plus, and I'm going to put a negative here, and then I'm going to factor out the theta double dot. Okay. And then what is left on the right-hand side? What is left is this Coulomb force, the friction term, and then the L1. Yeah. So plus MB L1 cosine theta, theta dot squared. Okay. That looks good. Now, let's take the other one that we had just a moment ago, and let's just write it up here. So it was negative, it's actually the same as this one. It was negative MB L1 sine theta, and that's times Q double dot this time. And then it was plus IZZBB plus MB L1 squared times theta double dot. And then this was equal to the external torque minus L1 cosine theta MB G. There we go. So what are we going to do with this now? Look at this and realize something. I've written it in this way for a very particular reason. What we're looking at is, these are nonlinear equations in the sense that we have things like L1 squared, and we've got theta dot squared. Inside of this friction term, there is the absolute value, and absolute value is discontinuous. But with respect to the unknowns, with respect to the Q double dots and the theta double dots, these are actually linear equations because we've been able to factor these out. So what if we rewrite this system as a linear system? Let's take these coefficients and put them, so MA, MB, and minus MB L1 sine theta, minus MB L1 sine theta, and IZZ BB plus MB L1 squared. And I'm actually going to erase the figure. We're done with that for now. And in order to get this coefficient matrix, we factor out the unknown accelerations. So factor these out. And then the right-hand side, this is actually just a vector of scalar terms. So FC plus MB L1 cosine theta, theta dot squared. These are all known, so they're just a number. And then the torque minus L1 cosine theta MB G. There we are. This is the same thing as the one underneath, so I'm going to erase on bottom. Next, you could think of these now as a coefficient matrix and a vector of unknowns and a bias vector. So this is like writing the linear system AX equals B. And of course, you can solve this kind of linear system for X by inverting A and multiplying both sides. So X is equal to A inverse multiplied by B. If you take this matrix and you invert it and you multiply by the right-hand side, you will solve for the unknown accelerations. Now, in the realm of dynamics, in the realm of controls, in modeling, dynamic system analysis in general, we call these things, they have some names, and they're usually not written as AX equals B. It's usually written as capital M times Q double dot equals, this is how I tend to write it, with the Greek letter gamma. Now notice that this gamma contains things like gravity. It contains friction quantities. If there were springs in this problem, it would contain springs as well. So sometimes you'll see this expanded and you might see something that looks like this. MQ double dot plus, let's write it as a capital D, D as a function of Q dot plus G as a function of Q equals F, something like this. Now, this is the same thing as what I've written above. These are the same thing. In fact, all of these are all the same things. It's just different ways to represent what is going on up here. So you have the specifics for your problem, and we can represent the specifics using this kind of general form for the equations of motion. And what I've done in the one on bottom is I have removed certain terms from the gamma, and I have brought them to the left-hand side of the equation. And the terms that I've brought over are damping and gravity terms, and we could even add in, more. We could add in spring terms on this side if we want. So let's say we do something with I don't want to use capital K, it's a linear momentum. Let's just use a B, right? And B could be a function of position as well, and F. So whenever you see these things in books, or whenever you see research papers, and they say, here are the dynamics for the problem, and they present it in some form like this, underneath that, they will go through and they'll say the M is the 2 by 2, and this is called a mass matrix. Mass matrix. In just standard math, you would call this the coefficient matrix, but it's the same thing, and it has the dimensions of n by n, where n is the number of degrees of freedom. In this problem, we had 2 degrees of freedom, so our matrix is a 2 by 2. So you have a mass matrix. This is your unknown generalized accelerations. This would be a damping term. This could be your gravity term. This could be your spring term, etc. I tend, unless I have a specific reason to do it, I tend to just take these things and put them all on one side and just put them in a vector like that. You also will see other names for these things. So let's go back to this one above it. Other things that you will see these called, this is called the whole thing on the left-hand side. This whole thing is the generalized inertial forces. And then the right-hand side, these are your generalized active forces. So all kinds of names for what these things are called, just depending on the textbook or the source that you are reading. So if you wanted to analyze this system, what would you do? You would go through the whole process that we just did. You would generate these equations. You would cast them in this kind of linear system, and then you can solve the whole system all at once for the generalized accelerations using this kind of linear solution. So Q double dot is equal to the mass matrix inverted multiplied by the vector of generalized active forces. And then what do you do with these? The Q double dots. Well, these are now accelerations, and you can integrate those to get velocities. You integrate the velocities to get positions. And if you do this inside of simulation, numerical integrators like Run-Kutta, there's RK4s, RK45s, this is like ODE 45, the function call in MATLAB if you're familiar with that, or Eulers method. It's a little more Stone Age than RK4, but that's how we put people into space. Okay, so this is done. If I say that I want the equations of motion, I need you to generate these equations. If you only do one of them, you're only halfway done. If I say I want the equations of motion represented in general form, it means I want you to put them into some kind of linear system representation like this. And now this is done because we have eliminated all of the unknowns in the problem. All right. So that's what equations of motion look like when you have multiple degrees of freedom. You end up with multiple equations, and you put it into this linear form. All right. So that is it for this video. Best of luck, everyone, and stay safe, and I'll see you later.